Today we are going to learn about the three postulates of the Bohr atomic model and expand a little about it. The first postulate of Bohr's atomic model deals with the energy levels of the atom. The first postulate of Bohr's atomic model states that an electron in an atom could revolve in certain stable orbits without the emission of radiant energy. Through the Bohr model, we know that the total energy of the electron En is equal to minus 13.6 divided by n square electron volts, where n is equal to 1, 2, 3, and so on. The n represents the energy level of the atom. If we substitute n is equal to 1, we get E1 is equal to minus 13.6 electron volts. If we substitute n with 2 and 3, we get E2 is equal to minus 3.40 electron volts and E3 is equal to minus 1.51 electron volts, which are the energies of second energy level as well as the third energy level respectively. The energy level of n is equal to 1 has the least energy, which is minus 13.6 electron volts, where the electron is revolving very close to the nucleus. This is the ground state of the atom. Now, to promote the electron from the lowest state to a higher energy state, we need to give the atom sufficient energy. This sufficient energy is the difference of the energy between a higher energy level to the lowest energy level, that is the ground state. For example, to promote the electron of an hydrogen atom from the ground state to the next energy level where n is equal to 2, the difference between the two energy levels is E2 minus E1 is equal to 10.2 electron volts. So, when we give 10.2 electron volts of energy to the atom, the electron is promoted to the second energy level. When the electrons are raised to a higher energy level, the atom is said to be in the excited state. We can do the same for the rest of the energy levels as well. Now, if we want to free the electron from the atom, we will consider the electron should reach the infinite energy level where n is equal to infinity. When we substitute n is equal to infinity to the formula, we get E infinity is equal to 0 electron volts. Therefore, the energy required to move the electron from the ground state to the infinite energy level, we need E infinity minus E1 is equal to 13.6 electron volts. This 13.6 electron volts is the minimum energy required to free the electron from the clutches of the nucleus. The minimum energy which is required to free the electron from the nucleus is the ionization energy. Let us study about the line spectra of the hydrogen atom. According to the third postulate of the Bohr atomic model, when an atom makes a transition from the higher energy level to a lower energy level, the difference in energy is released as a photon. To consider this statement in equation form, we get h nu if is equal to Eni minus Enf, where Ni is the higher energy level and Nf represents a lower energy level. Substitute the total energy formula. En is equal to minus me power 4 divided by 8 n square epsilon naught square h square, and put the common variables to one side. We get h nu if is equal to m e power 4 divided by 8 epsilon naught square h square into 1 by nf square minus 1 by ni square. We can write the equation as nu if is equal to m e power 4 divided by 8 epsilon naught square h cube into 1 by nf square minus 1 by ni square. This is the Rydberg's equation. Now, we know that the velocity of light c is equal to nu into lambda. If we write this in terms of nu, we get c by lambda. We can substitute nu in the above equation. Thus, we get 1 by lambda is equal to m e power 4 divided by 8 epsilon naught square h cube c into 1 by nf square minus 1 by ni square. The constants can be written as r, therefore the equation will be written as 1 by lambda equal to r into 1 by nf square minus 1 by ni square. The r from the above equation is the Rydberg's constant. When we substitute all the constant values, we get r is equal to 1.3 into 10 to the power 7 per meter. This value of r is close to the value of the r obtained from Balmer formula, where r is equal to 1.097 into 10 to the power 7 per meter. The Bohr model was in agreement with the Balmer series, and eventually it was also in agreement with the other series such as Lyman series in the UV region, Pasten series in the infrared region, Brackett and Fun series in the far infrared regions. The lines which arise due to the transitions from higher energy levels to first energy level is grouped as Lyman series. Similarly, the lines obtained as a result of transitions of electrons from higher energy levels to second, third, fourth, and fifth energy levels give rise to Balmer, Pasten, Brackett, and Fun series, respectively. Various lines are produced when the electrons jump from a higher energy state to a lower energy state, thus emitting photons in the process. These lines are called as emission lines. But when an atom absorbs photons that has the same energy that is needed to jump from a lower energy level to a higher energy level, this process is called as absorption. Now we are going to learn about de Broglie's explanation of Bohr's second postulate of quantization. Bohr's second postulate states that the angular momentum of the electron orbiting around the nucleus is quantized as Ln is equal to nh by 2 pi, where n is equal to 1, 2, 3, and so on. In 1923, de Broglie explained that material particles such as electrons also have a wave nature. Consider waves traveling on a string. The particle waves can lead to standing waves under resonant conditions. When a string is plucked, a vast number of wavelengths are excited. However, only those wavelengths survive which have nodes at the ends and form the standing wave in the string. It means that in a string, standing waves are formed when the total distance traveled by a wave down the string and back is one wavelength, two wavelengths, and any integral number of wavelengths. Waves with other wavelengths interfere with themselves upon reflection and their amplitudes quickly drops to zero. For an electron moving in nth circular orbit of radius Rn, the total distance is the circumference of the orbit, that is 2 pi Rn is equal to n lambda, where n is equal to 1, 2, 3, 4, and so on. For a standing particle wave on a circular orbit, the n will be equal to 4. Therefore, the equation can be written as 2 pi Rn is equal to 4 lambda. Here, lambda can be written as h by p, where p is the magnitude of the electron's momentum. If the speed of the electron is much less than the speed of light, the momentum is hvn. Therefore, lambda can be written as h by mvn. This lambda can be substituted in the above formula, where 2 pi Rn is equal to nh by mvn, or mvn Rn is equal to nh by 2 pi. This is an explanation for the second postulate of Bohr's atomic model. Limitations to the Bohr's atomic model. The Bohr's atomic model is applicable only to hydrogenic atoms. It cannot be extended even to atoms with more than one electron in it. The formulation of Bohr's atomic model involves electrical force between positively charged nucleus and a negatively charged electron. It does not include electrical forces between two or more electrons, which necessarily appear in multi-electron atoms. While the Bohr's atomic model correctly predicts the frequencies of the light emitted by hydrogenic atoms, the model is unable to explain the relative intensities of the frequencies of the spectrum. In emission spectrum of hydrogen atom, some of the visible frequencies have weak intensities, while others have strong intensities. These are a few limitations of Bohr's atomic model.